Okay, hey folks, how we doing? So getting into this chapter 5 on simple mixtures. So I am expecting kind of a pretty quick turnaround time on this chapter because we do need to get kind of caught up. But also this is a relatively short and sweet and simple chapter. So this will be largely conceptual, not a whole lot of math from this chapter. And I doubt that I will generate any Igor activities from this chapter, but there's still some really cool chemistry going on here. So partial molar quantities. So you're already familiar with one partial molar quantity, and that's partial pressure, right? In Dalton's law of partial pressures. But something that I'm going to get into that you probably haven't talked so much about is the partial molar volume, and that is the partial molar volume from a simple mixture. So we recognize this partial molar quantity is for a simple mixture. Okay, so partial molar volume I will define as V sub J, where J is a subscript denoting a chemical identity. Okay, and because this is a partial quantity, right, this is the partial of V with respect to the partial of number of moles of species J. And this is with a bunch of stuff being held constant: pressure, temperature, and N prime. N prime meaning the total number of moles in my mixture is constant. Okay. So for example, if I have a mixture of J and K, so N prime is Nj plus Nk. So the totals of those are constant, but we recognize that I can either vary the number of moles of J in my mixture, or I can vary the number of moles of K in my mixture such that they add up to a mole fraction that's always consistent. Okay. So for example, the mole fraction of J is going to be Nj over N prime. All right. And so let's suppose that we mix species A and B together. Okay. And you can see I've got this graph of ethanol and water. So maybe A is ethanol and B is water, for example. Okay. If I now want to talk about my total change in volume of this mixture, so the total change in volume that happens when I mix infinitesimally small quantities of these two, then I can expand this as the following. So the partial volume of species A with P, T, and N, B, of course, being held constant now to make to hold that constant. Okay. And then actually, you know what? I'm realizing this is probably getting confusing. So let's get rid of this and we'll stick to this notation. Okay. So for partial of NA, we're going to hold NB constant, and then it'll be that case for the other partial derivative. Okay. And then DNA, DNA. And then now we've got the partial of V with respect to the partial of B, and now that's P, T, and N. A is being held constant. So that's where you get that overall, the total number of moles will be constant, but we're varying which one, right? A or B, okay? And so I can write this succinctly as dV equals V sub A dNA plus V sub B dNB. Okay, so these two are equivalent expressions with the way that I've written them. And what we note, as we change the amounts of A and B, the prevailing intermolecular forces of the solution change. And this leads to a different thermodynamic environment. Okay. So how does this manifest? Well, if we look at here, we've got a mixture. where there's mole fraction on the x-axis, okay? And we note here that, I'll draw a second axis above. If this is for mole fraction of ethanol, right, 0 and 1, then up top I could write mole fraction of H2O, for example, so chi. And when a mole fraction of ethanol is 0, the mole fraction of water is 1, right? And when the mole fraction of ethanol is 1, the mole fraction of water is 0. So keep that in mind when we start looking at these graphs, okay? And what I'll point out here is in the limit of only having a solution of water, right, mole fraction of 1.0, look at the value for water, 18 cubic centimeters per mole. And if you recall, we've been calculating these partial molar quantities, right? And we even did that for, mind blanking, we did that for phase diagrams, right? And so this is the same thing as when we calculated that 0.018 liters per mole for pure water, okay? And what we note now is as we start adding ethanol, there's some really interesting things that start happening, right? So there's this particularly interesting thing that's occurring at a mole fraction of about 0.1. So the water is swelling as a result. The ethanol is compressing, okay? And as we scan across here, we can see that now our partial molar amount of water is really going to diminish as it gets diluted out, which makes sense. To now the point where we have a pure ethanol solution, and we would calculate a pure ethanol solution should be 58 cubic centimeter per mole, okay? So these partial molar quantities are definitely 100% dependent on what they are being mixed with. And as a result, this is typically empirical, okay? So moving along. So now if let's say I want to make some calculations as to what the volume should be, what the actual volume of my solution should be, then I'm going to integrate from 0 to the number of moles of A, VA, D in A, okay? And then I also integrate from 0 to the number of moles of B times VB, D in B, and this just simply gets me the partial volume of A times its number of moles plus the partial volume of B times its number of moles, right? And if we expanded this into being an ideal gas, right, then we would actually arrive at Dalton's law of partial pressures, where we're just adding up the individual contributions of pressures. In this case, since we did this for a solution, or at least this example, right, this would give me the same thing, right? The amount of A times its volume plus the amount of B times its volume would give me the total volume of the solution, okay? What also becomes cool, if I go now to this partial molar quantity, and I'm going to give you an example for partial molar quantities of magnesium sulfate aqueous, which I'll remind you would be partial of V, partial of N of the number of moles of magnesium sulfate. I'm going to drop writing that aqueous because what I'm going to write in its place is P, T, and then the number of moles of H2O is constant. So this is just a really interesting example that I want to bring up here. You actually get a negative number for this one. Okay, so you actually get negative 1.4 cubic centimeters per mole at near dilute concentrations. Okay, near dilute. So what does that mean? Well, if you look at this graph right here, volume versus amount added, you notice that there are regions in which there's a positive slope, and there's some regions in which there's a negative slope. And so magnesium sulfate, aqueous solutions of magnesium sulfate, have this example where you see a negative slope for the partial molar volume. So what does that mean physically? Well, magnesium sulfate is a drying agent. Okay, so those of you that are good with your organic chemistry, remember that if you want to dry out water in a mixture, you can add magnesium sulfate, and that complexes the water, right? It makes a hydrate. So the effect of that is it actually reduces volume from our solution. For every mole of magnesium sulfate added to an aqueous solution, it will reduce the volume by 1.4 cubic centimeters, which is pretty cool, right? So again, what this means is if I had a beaker containing, let's say, 100 mils of just pure water, and now I add 1 mole of magnesium sulfate to this, I'll no longer have 100 milliliters. I'll have something like, can I do this math? 98.6 milliliters, right? It'll actually reduce the volume, which is really cool, okay? And so that's, for this number, that's in the limit of near dilution. So that's like when this is approaching the end of this curve, okay? And so now, because of all of this being empirical, there's no like definite given relationship for this solution and that solution. You have to measure it and find out. Typically, polynomials are used to fit mixtures. So in other words, like if I want to know this total volume, if I want to predict this, so you can see this equation is kind of crazy looking. So I would need to use some type of polynomial like A plus B. Let's say if I was doing this on a mole fraction graph, it would be A plus B times mole fraction plus C times mole fraction squared plus D times mole fraction cubed, etc. Okay? So there's no definite given equation for how to predict partial molar volumes of these solutions. You have to just mix them little bits at a time and look for changes in volume. And of course, then fit the data with a polynomial to get after that quantity. I'm not going to really have you do much with that, but it's an interesting example all of the same, where you can actually add a solid to a liquid and it reduces the volume. It's counterintuitive, right? Okay, so of course we could also talk about partial molar Gibbs free energy. So partial molar quantities can be a lot of different things. We've talked partial pressure very briefly, but that's an example I think you already know about. Partial molar volume, and now partial molar Gibbs energy. Okay, so I'll remind you that the molar Gibbs energy is chemical potential. And similarly, I could also just say G equals mu times dN, right? So if we know that molar free energy, which is really G divided by dN, right? Then I just did some algebra here, okay? And so what that means then, my chemical potential, believe it or not, is a partial molar quantity. So just plain chemical potential of species J, whatever it is, water, ethanol, whatever you want, okay? So that is the partial of G with respect to the partial of the number of moles of species J. And of course, that's all at constant pressure, constant temperature, and assuming that the other component is at constant number of moles as well, okay? So, of course, then I could write the total differential for G in my mixture. If, let's say, I'm mixing A and B, back to just another simple example, okay? Mix A and B. So then I'm going to have now the partial free energy of A, which is the chemical potential of A, okay, at constant T, constant P, and constant NB, and then times dNA, and then now that's going to be partial of G by partial moles of B, so the chemical potential of B. And that's at constant T, constant P, and constant NA, and this is, of course, going to be dNB. Okay, such that now I could write my Gibbs free energy at constant temperature and pressure equals just simply mu A NA plus mu B NB. So it reduces to that simple equation right there, which is what I see right here. Okay, so free energy versus amount added. And you can see that there, in this example, this is showing you all like positive slopes. But of course, we could imagine situations, in which the free energy has an effect where there's a negative slope. Okay, and so the effect of that, of having a negative slope right there, that would actually tell us that there's a benefit to adding that particular species to this other species. So it would tell us there is a strong interaction between A and B if it's lowering the chemical potential. Of course, now in this figure here, as B and A are being added together, if it's raising the chemical potential, of course, that tells us it would be non-spontaneous, right? Because we need to see Gibbs as a negative for spontaneous mixtures. So we're going to come back to this in a bit, talking about spontaneity in mixtures and forming solutions. Okay. So, and now there's a really important equation that manifests if T and P are not constant. So if T and P are not constant, we end up with a really important equation in thermodynamics. So this goes dG, and we have to remember the fundamental equation that happens when we combine the first and second law. And so that's going to go V dP minus S dt plus the sum of all chemical potentials of species I, so the sum like I, J, K, L, however many things are in our mixture, times the change in number of moles, okay? And so now this equation, I'm going to box this, and I'm going to call this the fundamental equation of chemical thermodynamics, because there's just not a whole lot of chemistry we can do if we're not accounting for how the number of moles changes. So up to now, we were playing with this equation, dG equals VdP minus SdT, and that created our basis for phase equilibria. Well, when we actually add in this chemical potential and changing number of moles, that is what's going to create our basis for understanding the thermodynamics of mixtures, but also creates the basis for understanding what happens to dG with chemistry. Okay, so this is pretty cool. So what do I have on the next slide? So there are other partial molar quantities that we have. I didn't leave myself very much room to write, so I'm going to write them up here in the top. So we could talk about all of these chemical potentials now could actually be given not just by G, but by the other quantities depending on what's being held constant. So for example, we could say the chemical potential of J is the partial of U by the partial of number of moles of J. And because this is U, we have to quickly think about our thermosquare, that UG ship. We remember that U would be sandwiched between S and V. Okay, so if S and V are being held constant, my chemical potential is related to internal energy. So let me kind of box this off right here. Okay, so let's see here, I could make a chemical potential out of enthalpy if I hold entropy and pressure constant. All right. And I could make a chemical potential out of a partial molar quantity with the Helmholtz free energy if I hold T and V constant, okay? And so, so here I've got now the partial molar quantity for Gibbs, okay? So we can talk about these chemical potentials, not just with respect to free energy, with Gibbs free energy, but we could talk about them with respect to the Helmholtz free energy, to the enthalpy, and the internal energy, depending on what we're holding constant. Okay? So, but this is the one for chemists, dG, and that's because of the dependence of P, T, and number of moles. Okay? So that is truly giving us the grand canonical ensemble. Okay? So for those of you that go on to do thermo in grad school, you'll get into those ensembles. Remember, the canonical, the microcanonical, and the grand canonical. Okay? So let's keep going. Alrighty. So the thermodynamics of mixing. So I'm not going to spend a lot of time deriving these equations here. But what I do want to talk about with respect to ideal gases, this is going to create our basis for understanding the thermodynamics of mixing. And when you mix ideal gases, it is, I can't write. It is always spontaneous, right? So think about that. If I have a cylinder of oxygen and a cylinder of nitrogen, and I just both open them up and let them fill a room, they're going to mix with each other spontaneously. So in other words, delta G of mix for ideal gases is always less than 0. And you can actually see this graphed right here. Okay, so I'm going to show you where this equation comes from in a minute. But what's really cool is, again, suppose we're mixing gases A and B, and we then calculated the free energy of mixing. You would actually find it hits a maximum negative value at exactly a 50-50 mixture, which makes good sense when you think about that maximum free energy. And notice here, though, that all of the values are negative, which makes sense. Mixing ideal gases in any quantity will be spontaneous. Okay? So where does this come from? Well, we derived an equation previously, okay, where and this came from the phase changes slides, where I said the chemical potential equals the standard chemical potential plus RT natural log and pressure divided by standard pressure. If you're like, where the hell did that come from? Don't worry about it. I'm not going to hold you responsible for deriving this or anything, but this did come from the phase changes section. Okay. And so now, of course, we recognize then that free energy, right, as we just discussed, is going to be mu of A times N of A plus mu of B times N of B. And now we recognize that I have an equation for chemical potential, which I could supply into each one of these. And furthermore, we also recognize that delta G of mixing is going to be G final minus G initial. Then what that means is this equation, GI, would give me the initial free energy. Then I could write the final energy, right? And then subtract them, and so on and so forth. And again, I'm not gonna like make you responsible for where this gets derived from. But what we would come up with for an ideal gas. So the book always writes delta mix G, and I don't like writing it that way. I like writing delta G mix. Okay. What we would get is the following. Okay. It would end up being nRT. And actually, in my fall 2019 notes, which I've posted, the full derivation of this equation is available right there if you're curious. Okay. But what we would get is nRT times the following. Chi A, and so I'll remind you, the mole fraction of A is going to be the number of moles of A divided by the total number of moles, okay? And then that's going to be the natural log, so chi A times the natural log of A, plus chi B times the natural log of chi B, okay? And so if we inspect this equation really quick, we note that because these mole fractions are always less than 1, right? that means my natural log is always going to be a natural log of a number less than 1, which gives me a negative. So this equation will always be negative. So mixing ideal gases is always spontaneous. Okay. So we also recall from our thermo square and our Maxwell relations that the partial of Gibbs free energy with respect to temperature at constant pressure, and then now I'm going to tack in that number of moles, okay, is negative entropy. So from this relationship, I can quickly come up with delta S of mixing gases, right? And so that's just going to be given by now taking this equation with respect to dt, so taking the first derivative with respect to t. And of course, there's a negative sign in there. So then that's going to become negative in R. The t drops out because I'm taking the derivative of this equation with respect to t. And so now that just becomes negative in R chi A, natural log of chi A, plus chi B, natural log of chi B. And a quick inspection you'll realize that this equation is always greater than 0 because of the same relationship here of these mole fractions. The natural log of a number less than 1 is negative, but now I have a negative sign right there. So negative, negative gives me a positive. And then this is what we would see for entropy. We would see always a positive value. And again, we remember that criterion for spontaneity. Free energy has to be negative and entropy has to be positive. And similarly, we would also see the maximum entropy occurs when the mixture is 50-50. Okay? So then now, what about delta H of mixing? Well, we recognize that delta G of mixing is just going to equal delta H of mixing minus T delta S of mixing. So that comes from remembering that G equals H minus TS. All right? And if you think about this, if I were to plug this in for delta G, right? And I were to plug in this for delta S, well, look what's going to happen, okay? They become equal and opposite, and the result is delta H of mixing an ideal gas is always 0, okay? So there's no heat released or absorbed when two things mix, and this is actually going to create our basis for understanding how liquids mix, okay? So we've established for ideal gases, they always mix spontaneously, and there's no enthalpy change when they do mix. And that is going to allow us to think about what happens to a solution when we mix a solution, okay? So let's see here. So I'm going to keep going because that was a nice description right there. We're getting right on the money here with this ideal solutions, okay? Which again, as I said, is going to create the basis for understanding that delta H of mix must equal 0, okay? But also, what about what happens to the vapor pressures and other partial quantities when we do this mixture, okay? And so as I'm looking at the time, I see I've been talking for about a half an hour. I'm actually going to leave it at that. So I think I said I was going to try to do 2 videos. I think I'm going to try to do 3 shortish videos, okay? So what I talked about in this video was be familiar with partial molar quantities, okay? Know the fundamental equation of chemical thermodynamics. So I want you to know that equation. And then be familiar with the mixing of ideal gases. And that's a good place to leave it. And so now what I'm going to come up with on the next video is going to be more on now mixing of solutions, okay? Or mixing of liquids, rather. Okay, folks, I'll see you in the next video.